In 1859, a solar storm set telegraph wires on fire, threw the northern lights down into the tropics, and proved that our star could reach across 93 million miles and touch our technology directly. We called it the Carrington event, and we have spent every year since quietly hoping it never happens again. But a new study has just handed us a reason to look up nervously, because it found that the sun's magnetic engine is reorganizing in a way that hides its true strength behind a calm-looking face, exactly the kind of face our star was wearing in 1859. 1859, all over again, may not be a question of if, but of when, and of whether we would even see it coming. If stories like this are why you are here, subscribe to the Sky Lab and tap the like button to help more people find it. Tell me in the comments where you're watching from, and whether you think our power grid is ready. Now, let's get into it. Part 1. The Quiet Sun. That isn't. Twice in the last 2 weeks, the forecasters told us a storm was coming. Twice the warning climbed all the way to the second highest tier on the scale, the level they call strong, the level that can push the northern lights down into states that almost never see them and put a quiet strain on the power grid. And twice, almost nothing happened. The cloud of charged gas that was supposed to slam into us slid by instead. We caught a shock wave, a faint shudder in the planet's magnetic field, and then the needles went still. If you were outside with your camera waiting for an aurora, you probably went back indoors disappointed. By every ordinary measure, it was a non-event. The sun threw its punch, and the punch missed. Most people read a story like that and feel a small, comfortable relief. The big, scary forecast didn't pan out, the light stayed on, the sky stayed dark, and life went on. And that reaction is completely understandable. But I want you to sit with a different question for a moment, because it is the question that this entire video is built around, and it is the question that a group of scientists just answered in a way that almost nobody is talking about. The question is not why the storm was so weak. The question is why it missed. Because there is a version of a missed storm that is genuinely reassuring, and there is a version of a missed storm that should make the hair on your arm stand up. And the difference between those two versions is the difference between a sun that is settling down and a sun that is quietly learning how to aim. For as long as human beings have studied the sun in any serious way, we have judged its mood by its face. We count the dark spots. When the spots are many and large and tangled, we say the sun is active and dangerous. When the spots are few and small, we say the sun is quiet and safe. That habit goes back centuries, and it is baked into almost every forecast, every news story, every headline you have ever read about solar activity. More spots, more danger. Fewer spots, less danger. It is simple, it is intuitive, and right now it is telling us that the sun is on the calmer side of average. I want you to notice how completely that one habit has shaped the way all of us think about our star, because it is the assumption this whole video is going to challenge. Every time you have seen a headline announce that solar activity is ramping up or winding down, somebody made that call by looking at spots. Every forecast of a quiet stretch or a stormy one leans at bottom on that same count. We have trusted it for so long, and it has worked well enough for so long, that we have stopped treating it as a measurement at all, and started treating it as the truth itself, as if the spots were the danger rather than a symptom of it. But a symptom is not the disease. A thermometer reading is not the fever, it is just the part of the fever we happen to be able to see. And for the whole history of solar science, the spotted surface has been the only thermometer we had, the only part of the sun's inner state that revealed itself plainly to a telescope. So we built our entire sense of safety on the one reading we could take, and we quietly assumed that reading told us everything that mattered. The moment a second independent instrument comes along and starts disagreeing with the first one, that assumption is exactly what gets called into question, and that is precisely the situation we are now in. We have a new way of reading the sun, and it is not agreeing with the old one. The current cycle has not produced an especially spotted sun. By that one number, the number we have trusted for hundreds of years, there is nothing here to worry about. And that is exactly where this story turns, because a team of scientists decided to stop looking at the sun's face and start listening to its insides. They spent nearly 40 years recording something most of us never think about, a sound the sun is constantly making, a low ringing that travels through its interior the way a struck bell rings through metal, and when they finally laid 4 decades of that ringing side by side and sorted it out, they found something that the spotted surface had been hiding from us the entire time. They found that the engine driving the sun's 11-year heartbeat has been changing. It has been moving. It has been creeping upward, concentrating itself into a thin layer just beneath the surface, into a shell barely 1,000 kilometers thick on a star that is more than 1,000,000 kilometers across. And the part that should stop you cold is this. That shell sits in exactly the place our oldest, most trusted instrument cannot properly see. So we have a sun that looks calm on its face, and a sun that is doing something unusual just beneath that face, and a way of measuring it that disagrees with everything the spot count is telling us. If that were the whole story, it would still be one of the most interesting things to come out of solar physics in years. But it is not the whole story, because this discovery did not arrive in a vacuum. It arrived in the same few weeks that the sun has been firing off those tightly aimed eruptions that keep sliding past us. It arrived while a long-lived hole in the sun's atmosphere has been sweeping a stream of fast solar wind across the planet again and again, and it arrived at a moment when the thing a great solar storm would actually threaten. The electrical skeleton of modern life has never been older, never been more loaded, and never been more exposed than it is right now. Here is the thread I want you to hold on to, because every single part of this video hangs from it. For 100 years and more we have measured the danger from our star by counting the spots on its skin. But the danger may no longer live on the skin. It may have moved underneath, into a place our counting cannot reach. And if that hidden change is making the sun's eruptions tighter, narrower, more focused, then the storms that keep missing us are not a sign that we are safe. They are a preview. They are the sun practicing its aim on an empty target, and a near miss is only ever one small turn away from a direct hit, on a civilization that has wired itself more tightly to the electrical grid than any civilization that has ever existed. I know that sounds dramatic. I am going to spend the rest of this video showing you that it is not exaggeration, it is arithmetic, and I am going to do it the way we always do it here, by walking through the actual data, the actual study, the actual history, and separating what is solid from what is speculation at every single step. We are going to talk about how you can possibly listen to the inside of a star. We are going to talk about what these scientists actually heard and why it broke the pattern of the last 4 cycles. We are going to talk about the 2 storms that just missed, and the geometry that explains why, and the unsettling thing that geometry implies. We are going to walk through the 3 times in recorded history that a storm like this did not miss, and what each one did to the world of its day. And we are going to look, very honestly, at how exposed we are now, and at all the things this is not, because there is a lot of nonsense attached to this subject, and we are going to clear it away. But before any of that, you have to understand the instrument, because the whole discovery rests on it. You cannot cut the sun open. You cannot send a probe into it. Every photograph you have ever seen of the sun shows you nothing but its outermost skin, the thin, bright layer where light finally escapes. Everything below that is sealed off from our eyes forever. And yet these scientists are telling us, with confidence, what is happening 1,000 kilometers down, in a region no telescope will ever photograph. So the first thing we have to answer, before we can trust a single word of what they found, is a question that sounds almost impossible. How do you listen to the inside of the sun? The answer is one of the most elegant tricks in all of science, and it starts with the fact that our star is screaming a note so low that no human will ever hear it. Part 2. How you listen to a star. The sun is ringing like a bell, right now, all the time, and it has been for billions of years. That is not a metaphor I am reaching for to sound poetic. It is a literal physical fact, and it is the foundation of everything we are about to discuss. The surface of the sun is not a calm, glassy sphere. It is a churning, boiling ocean of plasma, an ocean of gas so hot that its atoms have been torn apart into charged particles, and that ocean heaves and convects and crashes against itself with a violence that is almost impossible to picture. All of that churning sends pressure waves rippling down into the body of the star, the same kind of pressure waves that carry sound through the air to your ears. And just like sound trapped inside a closed pipe or a struck bell, those waves bounce around inside the sun, reflecting off its boundaries, overlapping and reinforcing each other until the whole star is humming with a set of standing tones. Now, you will never hear those tones, and not just because you would need to be standing inside the sun. The note the sun rings at is far, far too low for any human ear. The strongest of these oscillations rises and falls over a period of about 5 minutes. Think about that. A single vibration that takes 5 minutes to complete one cycle. Your ears can detect sounds that vibrate a few dozen times per second at the very lowest end. The sun is vibrating once every 5 minutes. It is a note so low that compared to it, the lowest pipe on the largest cathedral organ on Earth is a shrill little whistle. But low or not, it is a real measurable vibration, and that is the key that unlocks the entire interior of our star. Here is why that matters so much, and here is the trick that turns a useless, inaudible hum into one of the most powerful tools in modern astronomy. When a wave travels down into the sun, it does not go straight to the centre and stop. It bends. The deeper it goes, the hotter and denser the material becomes, and that change in conditions curves the wave's path, the same way a ray of light bends when it passes from air into water until eventually the wave turns around and comes back up to the surface. And the crucial part is this. The note of the wave, its frequency, determines how far it dives before it turns around. Some notes are shallow divers. They dip just under the surface and come right back. Other notes are far divers. They plunge most of the way to the core before they curve around and return. So every single tone in the sun's ringing has been to a specific depth and no further, and when it comes back to the surface, it carries information about the conditions it passed through down there and nowhere else. That is the core of it. That is how you listen to the inside of a star you can never cut open. You do not need to see inside. You just need to catch the notes coming back out, measure each one with absurd precision, and read the depth of its dive in the tiny shifts of its frequency. A note that comes back slightly sharper or slightly flatter than it should be is telling you that something changed at the exact depth that note travels to. We have a name for this entire field of study. We call it helioseismology, from the same root as the seismology that geologists use to read the inside of the Earth from the way earthquake waves travel through it. The Earth's interior is mapped by the shaking of quakes. The sun's interior is mapped by the ringing of its own restless surface, and the people who have been doing this the longest, with the most patience, are the ones who just handed us this discovery. The instrument they used has a name that tells you exactly what it is. It is called the Birmingham Solar Oscillations Network, and an oscillation is just a fancy word for a vibration, for the rising and falling of those solar tones. It is a ring of small, dedicated telescopes spread out around the planet in different countries, on different continents, positioned deliberately so that as the Earth turns and the sun sets on one station, it is already high in the sky over the next. Because here is the problem they had to solve. To hear a note that takes 5 minutes to vibrate, and to hear the slower, deeper notes underneath it, you cannot afford to stop listening every night when the sun goes down. A gap in the recording is like taking your stethoscope off the patient's chest every few seconds. You lose the rhythm. So they built a network that hands the sun off from one telescope to the next, around the clock, around the calendar, so that the recording almost never stops. And they have been doing this unbroken vigil, for nearly 40 years. 40 years is the number I want you to hold on to, because it is what makes this discovery possible, and it is what makes it so hard to argue with. The sun's main heartbeat, the rise and fall of its activity from quiet to stormy and back, runs on a cycle of about 11 years. So 40 years is not one cycle. It is 4 of them, stacked back to back. The scientist could line up the sun's interior voice during the cycle of the late 1980s, and the cycle of the early 2000s, and the cycle of the 2010s, and the cycle we are living through right now, and compare them directly, note for note, depth for depth. That is an extraordinary thing to be able to do. It means they were not looking at a single snapshot and guessing. They were watching a slow change unfold across 4 decades, across 4 heartbeats of the sun, and asking a simple question. Has the inside of the sun been doing the same thing each cycle, or has it been changing? To answer that, they did something clever with all those returning notes. They sorted them into groups by how far down each one dives. Remember, the frequency of a tone tells you its depth, so they took the lowest, deepest diving notes and put them in one group, the notes that travel down past about 3,000 kilometers below the surface and bring back news from those depths. They took the middle notes and put them in a second group, the ones that turn around shallower than 3,000 kilometers, and they took the highest, shallowest notes and put them in a third group, the ones that barely dip below the surface, that turn around within about 1,000 kilometers of the top. 3 groups, 3 depths, a lower listening post, a middle listening post, and a shallow listening post, all reporting at once, all built from nothing but the sun's own ringing. And this is why this method is so important for the question we started with, the question about the calm-looking face of the sun. The sunspot count, the thing we have trusted for centuries, only ever tells you about the surface. It is a count of features on the skin, but this method does not depend on the skin at all. It is an independent witness, a second opinion that comes from inside the patient, from depths the spot count knows nothing about. So when this method and the sunspot count start to disagree, that disagreement is not noise to be smoothed over. It is the most interesting signal in the whole field, because it means one of our witnesses is seeing something the other one cannot. And when these scientists finally laid 4 decades of the sun's 3-depth voice side by side, sorted and stacked and ready to read, the lower listening post, the middle listening post, and the shallow listening post were not telling the same story anymore. The shallow post had grown louder, the middle post had gone quiet. And the pattern those two facts make, when you put them together, is the thing that changes how we should read every calm-looking sun from now on. It is worth pausing on just how delicate this measurement actually is, because it tells you why it took a network like this and 40 years of patience to pull it off. The frequency shifts we're talking about are not dramatic, sweeping changes. They are minute, a fraction of the note's pitch, the kind of difference you could never hear and could only ever measure with instruments built for the single purpose of watching the sun's light flicker with extraordinary steadiness. And there is not just one note. The sun rings in millions of overlapping tones at once, a whole orchestra of standing waves layered on top of each other, and the scientists have to disentangle that chord into its individual strings, track each one, and watch how its pitch drifts over years. The reason they treat the sun as a single point of light, rather than mapping its disk in detail, is that these particular global tones are best read by watching the whole star pulse in and out as one, the way you would feel a struck bell hum in your hand rather than studying one spot on its rim. That is why the method has a quiet kind of authority. It is not reading a fashion in the data or a quirk of one instrument. It is reading the integrated voice of the entire star, measured the same careful way, by the same patient network, across 4 decades and 4 cycles. When a measurement that stable and that independent starts disagreeing with the spot count, you do not get to wave it away. You have to ask what it is seeing that the old method cannot. Part 3. The mismatch. Let me show you the current solar cycle through the eyes of the old instrument first, the sunspot count, because you need to feel how reassuring it looks before I take that reassurance away. The cycle we are living through is the 25th one that scientists have numbered since they started keeping careful records. By the count of spots, it has been a fairly modest affair. It rose to its peak with a monthly spot number a little above 200 in the late summer of 2024, which is a touch stronger than the average cycle, but nothing that would make a solar physicist gasp. The radio brightness of the sun, another standard surface gauge that tracks how active the star is, has been similarly unremarkable. If you read this cycle the way we have read every cycle for centuries, you would file it under ordinary, lean toward the quiet side and move on. There is no alarm here. The face of the sun has been, by historical standards, well behaved. Now let me show you the exact same cycle through the ears of the new instrument, through the sun's interior voice, and watch the picture invert. The scientists looked at the shallow listening post, the highest notes, the ones that turn around within about 1,000 kilometers of the surface. And what they found is that during this supposedly modest cycle, those shallow notes shifted just as strongly as they did during one of the most powerful cycles of the entire modern era, the cycle that peaked back around 1990, the one numbered 22. Sit with that for a second, because it is genuinely strange. By its face, this cycle is ordinary. By the voice of its shallow interior, this cycle is shouting as loudly as a giant. The two measurements are not just slightly out of step, they are pointing in opposite directions. The surface says quiet. The shallow interior says this is one of the strongest signals we have ever recorded, and it gets stranger because the shallow post was not the only one that changed. The middle listening post, the notes that dive down past the shallow layer but turn around before 3,000 kilometers, did the opposite. Across the last 3 cycles, those middle notes have grown steadily less sensitive, steadily quieter, as if whatever they were responding to has been fading away beneath them. So picture the two trends together. the shallowest layer, right under the surface, has been getting louder and louder, until in this cycle it rivals the strongest cycle on record. And the layer just below it has been getting quieter and quieter across the same stretch of time. One layer waking up, the layer beneath it going to sleep. That is not random. That is a pattern with a direction, and the direction is up. The action is climbing toward the surface. When you put those two facts side by side, the conclusion almost assembles itself, and it is the conclusion the scientists reached. The engine that drives each solar cycle, whatever it is that organizes the sun's magnetism and pushes it through its 11-year rhythm, has been migrating upward across the last 4 cycles. It has been concentrating itself into an ever thinner shell, ever closer to the surface, until in this cycle the bulk of the structural change is happening within about 1,000 kilometers of the top. On a star that is nearly 700,000 kilometers from center to surface, 1,000 kilometers is nothing. It is a skin. It is the last thin layer before the light gets out. The sun's interior machinery has, in a sense, surfaced. It has come up out of the depths and pressed itself against the underside of the visible world. Now I want to be very careful and very precise here, because this is the single most important sentence in the entire study, and it is easy to get it wrong in a way that overstates things. The scientists did not simply say the sun's magnetic field got stronger near the surface. They were sharper than that, and the sharpness matters. They pointed out that if the only thing that had changed was the strength of the field down there, you would expect the size of all the frequency shifts to change together. A stronger field would push all the notes around more, but that is not what they saw. What they saw was a change in which depths respond at all, a change in the sensitivity of the shallow notes versus the lower ones. And the only way to get that, they argued, is not a change in how strong the field is, but a change in how it is confined, in how tightly it is packed into a particular range of depths. Their own words point to a change in the radial confinement of the field. Not how strong, where. The field has been squeezed into a narrower band, closer to the surface, and that squeezing is the thing the sun's voice has been recording for 40 years. Let me give you a picture for that, because radial confinement is a mouthful, and the idea underneath it is simple and important. Imagine a furnace in the basement of a large house, and imagine you are upstairs trying to figure out how hot it is by feeling the floor. For years, the furnace sits far down in the basement, and the floor upstairs feels only faintly warm, because the heat has a long way to travel, and it spreads out and fades on the way up. Now imagine that over time, without getting any hotter, the furnace slowly moves. It climbs out of the basement, up through the walls, until it is sitting just beneath the floorboards under your feet. The furnace has not gained a single degree. Its total output is the same, but now the floor is hot to the touch because the heat no longer has to cross all that distance. It is concentrated right there, just below the surface you can feel. That is what the data is describing. The sun's magnetic furnace has not necessarily gotten hotter. It has moved closer to the wall. I do not want you to skip past the comparison the scientists used, because the choice of cycle is not a random detail, and once you know what it means, it changes the whole emotional weight of the finding. They did not say the shallow interior of this cycle is shouting as loud as some forgettable middling cycle. They said it is shouting as loud as the cycle that peaked around 1990. The one numbered 22. And cycle 22 was not a quiet one. It was one of the most powerful of the entire modern era, a genuine heavyweight, and it is the very cycle that produced the storm that knocked out the power grid across an entire Canadian province in about 90 seconds, a storm we are going to walk through in detail later. So sit with what the measurement is actually telling us. By its spotted face, the cycle we are living through right now looks modest, ordinary, nothing to fear. By the voice of its shallow interior, it is ringing at the same intensity as the cycle that took down a grid and put millions of people in the dark. The face says one thing. The interior says it is in the same league as one of the most dangerous cycles we have on record. That is the core of why this study should change how you feel about a calm-looking sun, and not in a comfortable direction. We are not comparing today's sun to a sleepy, harmless one and finding a small surprise. We are finding that today's sun, the one the headlines keep calling weak, is matching a known heavyweight in the one measurement that reads its hidden magnetic state. If the shallow interior is the truer gauge, then the modest spot count is not telling us we are safe. It is telling us we are looking at the wrong dial. And the worst part is that the wrong dial is the only one most people, and most of the coverage, ever look at. The reassuring number on the surface and the alarming number underneath are describing the same sun, at the same moment, and only one of them is being reported. And here is where this loops straight back to the thread we started with, the thread about the calm-looking face. Our oldest instrument, the sunspot count, is a measurement of the floorboards. It reads the features that punch through to the very top, the dark blemishes on the visible surface. But this study is telling us that the structural change, the real action, has concentrated itself in the shell just underneath that surface. It is telling us that the furnace moved to a place where our flaw-feeling, spot-counting instinct does not give us a clean reading anymore. The cycle can look modest on its face, can produce an unremarkable number of spots, and still have its interior machinery in an unusual, concentrated near-surface state that the spot count simply does not capture. We have been judging the danger by feeling the flaw, and the furnace just moved. So we are left with a sun that is, in a real and measurable sense, two different suns depending on which instrument you trust. By the spots, it is quiet. By its interior voice, its magnetism has crept up and packed itself into a thin shell where it has never been this concentrated in all 40 years of listening. Both of those things are true at once, and that would be a fascinating piece of pure science even if it had no consequences at all, even if it just sat in a journal as a beautiful result about the inner life of our star. But it does have a possible consequence, and it is the consequence that turns this from an academic curiosity into the reason you are watching this video. Because if the sun's magnetic engine has moved up close to the surface and packed itself tight, the obvious next question, the question the scientists were careful not to overreach on but that we are absolutely allowed to ask, is what that does to the things the sun throws at us. What happens to a flare, to an eruption, to a billion-ton cloud of magnetized plasma, when the engine that launches it has relocated to the skin of the star and squeezed itself into a thinner, tighter, more concentrated form? To even begin to answer that, we have to understand what that engine actually is, and why where it sits might matter even more than how strong it is. Part 4. Why, where, beats, how strong. To understand why the location of the sun's engine could matter so much, you have to understand what the engine is, and I'm going to explain it the way I wish someone had explained it to me, without burying you in jargon. The sun is a ball of plasma, charged gas, and that gas is in constant motion. Down in the depths, enormous columns of hot plasma rise toward the surface, dump their heat, cool, and sink back down, over and over, the way water roils in a pot just before it boils. Now, here is the crucial ingredient. Moving charged gas generates a magnetic field, and a magnetic field pushes back on moving charged gas. So you have this churning, rising, sinking, swirling ocean of electrically charged material, and it is constantly generating, stretching, and twisting magnetic field lines as it moves. We call the whole self-sustaining process the solar dynamo, and it is the beating core of every storm the sun has ever thrown at us. It is the engine. Everything we see on the sun's surface, every feature, every outburst, is a symptom of that buried engine. A sunspot is a place where a bundle of intensely concentrated magnetic field has punched up through the surface, so strong that it chokes off the normal flow of heat and leaves a patch that is cooler and therefore darker than its surroundings. A solar flare is what happens when those tangled, stressed magnetic fields suddenly snap and reconnect into a simpler shape, releasing a stupefying amount of stored energy in minutes, a flash of radiation that crosses the distance to Earth in 8 minutes, and can disturb our upper atmosphere on arrival. And a coronal mass ejection, the thing we really care about in this story, is when that snapping magnetic field hurls an actual physical cloud of billions of tons of plasma off the sun and out into space, carrying its own tangled magnetic field with it. Spots, flares, eruptions, they are the smoke, the sparks, and the shrapnel of the engine, and the engine is magnetic. Once you see it that way, the importance of the new study reframes itself entirely. We spend almost all of our attention on the smoke and the sparks, on counting the spots and measuring the flares, because those are the parts we can see. But the spots and the flares are downstream. They are the output, the thing that actually determines their character, how concentrated they are, how violently they erupt, how the magnetic field is wound inside them, is the engine that produces them, and the engine lives below the surface where we have never been able to look directly. That is what makes a measurement of the interior so valuable and so unsettling when it disagrees with the surface. It is a reading of the cause rather than the symptom. For 100 years we have been forecasting the sun by studying its exhaust. Now for the first time, we have a way to listen to the engine itself, and the engine is telling us it has changed its configuration in a way the exhaust does not plainly reveal. When the part of the system that generates everything else starts behaving differently, you should care a great deal, even if the output has not visibly caught up yet, because the output always eventually reflects the engine. That is the whole reason this is worth a video and worth your attention. We finally found a window into the machinery, and through that window we can see the machinery rearranging itself. So now ask the question that the study forces on us. If that engine, the magnetic dynamo, has migrated upward and concentrated itself into a thin shell near the surface, what might that do to the spots and the flares and the eruptions it produces? And I have to be honest with you here, because honesty is the whole point of this channel. The scientists who did this study did not claim to know the answer to that question. They documented the change. They did not promise you a specific consequence. So everything I am about to say in this part is reasoning beyond their result, and I am labeling it as speculation clearly and on purpose. Because the difference between what is measured and what is guessed is the difference between science and noise. But it is reasonable, grounded speculation, and it goes like this. When a magnetic structure is buried far inside the sun, it has a long way to travel before it can erupt, and on that long journey upward it tends to get jostled, spread out and reshaped by all the turbulent plasma it has to pass through. By the time it breaks the surface, it has often been smeared into something broader and messier. But a magnetic structure that forms already near the surface, in that thin concentrated shell, does not have that long buffering journey. It is right there. It can emerge more abruptly, in a tighter, less smeared, more concentrated bundle. So if the engine has moved up, it is at least plausible, and I stress plausible, not proven, that the magnetic fields it produces could emerge more sharply and more compactly. And a more sharply concentrated magnetic structure is exactly the kind of thing that can launch a more sharply concentrated eruption. Hold that idea. We're going to test it against real, recent observations in a few minutes, because the sun has been giving us a live demonstration. But before we get there, I need to demolish a piece of false comfort, because it is the piece that lets people wave this entire subject away. The false comfort is the belief that a quiet-looking cycle, a cycle with a modest spot count, is automatically a safe cycle. That belief is wrong, and it is not wrong as a matter of opinion, it is wrong as a matter of recorded history, and I'm going to prove it to you with a specific event later in this video. But let me give you the principle now. The damage a solar storm does to Earth has very little to do with how many spots were on the sun that month. It depends on a handful of other things entirely. It depends on whether an eruption happens to be aimed at us or aimed off to the side. It depends on how fast the cloud is moving, because a faster cloud crosses the gap to Earth before it can spread out and weaken. It depends, more than almost anything, on the orientation of the magnetic field inside the cloud, because if that field points the right way when it hits us, it locks onto Earth's own field and pours energy in, and if it points the wrong way, it mostly slides off. And it depends on timing, on whether the sun has already disturbed our defences with an earlier blow before the main one lands. Not one of those factors is the spot count, aim, speed, magnetic orientation, timing. Those are what decide whether a storm is a shrug or a catastrophe, and a sun with a modest number of spots can get every one of them lined up in the worst possible way. This is the underlying reason the new study matters. It is not telling us the sun is about to explode. It is telling us that the one number we lean on to feel safe, the spot count, was always a crude proxy, and now we have evidence that this particular cycle is hiding an unusual interior state behind an ordinary-looking face. The calm of the surface was never a guarantee. It was always just the part of the sun we could most easily see. And now we have learned that the part we cannot easily see has been quietly rearranging itself. So when I tell you later about a storm that nearly matched the greatest one in recorded history, and did it while the sun had almost no spots at all, I want you to already understand why that's possible. It is possible because the spots were never the point. The magnetism was the point, and the magnetism lives underneath. The surface calm is not the same thing as safety. It may in fact be camouflage. A sun that looks sleepy on its face while its magnetic engine has crept up into a thin, concentrated shell just below is not a sun that is settling down for a nap. It is a sun whose readiness has moved into a blind spot in our oldest instrument. And the unsettling thing, the thing that takes this out of the realm of theory and into the realm of right now, is that the sun has spent the last couple of weeks behaving in a way that looks suspiciously like a live demonstration of exactly this idea. While the scientists were publishing a paper about magnetism concentrating into a tighter shell, the sun was firing off eruptions that came out tighter and narrower than the forecasters expected, eruptions so tightly aimed that they kept sliding right past us. The forecasters called for strong storms. The storms did not come, and the reason they did not come may be the single most important clue in this entire story, because the reason they missed is the reason a future one could hit so much harder than anyone is prepared for. There is one more piece of the puzzle that decides whether a storm is gentle or catastrophic, and it has nothing to do with size or speed, and everything to do with orientation. The cloud of plasma the sun throws at us carries its own magnetic field, tangled up inside it, and that field has a direction. When the cloud arrives, Earth's own magnetic field is standing in its way like a shield, and the crucial question is which way the cloud's field is pointing relative to ours. If the cloud's field points the same way as Earth's where they meet, the two mostly repel, the shield holds, and even a fast broad cloud can deliver a surprisingly mild blow. But if the cloud's field points the opposite way, southward, against our own, then the two fields link up, the shield effectively unlatches, and energy comes pouring through the opening into our magnetic environment. It is the difference between a key that does not fit a lock and a key that slides right in and turns. This is why forecasters can watch a big cloud approach and still not know how bad it will be until the last hour, when a spacecraft sitting between us and the sun finally samples the cloud's magnetic direction. A monster aimed straight at us with the wrong orientation can fizzle. A modest one with the right orientation, arriving on an already rattled planet, can punch far above its weight. Orientation is invisible from a sunspot count. It lives in the magnetic structure of the eruption, which is launched by the engine, which is the very thing the new study says has moved and concentrated. Every road keeps leading back to the same buried machinery, and to the same uncomfortable truth that the things which decide our fate during a storm are precisely the things the calm surface does not show us. Part 5. The surface is acting strange. 2. Here is something I find genuinely compelling about this whole picture. The interior study is not floating out there on its own, disconnected from everything else we can see. The visible surface of the sun, the part we can actually photograph, has also been behaving oddly for this point in the cycle, and the oddness all points in the same direction. It is as if the interior and the surface are two witnesses to the same event, and even though they speak completely different languages, they are describing the same change. So before we leave the engine and go look at the storms it has been throwing, I want to walk you through the surface clues, because once you see them lined up, the idea of a sun quietly reorganizing itself stops sounding like a leap and starts sounding like the obvious reading. The first clue is something called a coronal hole, and it has been a defining feature of this entire cycle in a way that is genuinely unusual. A coronal hole is exactly what it sounds like, a region in the sun's outer atmosphere where the magnetic field, instead of looping back down to the surface in closed arches, opens straight out into space like a chimney. And through that open chimney, the sun's outer atmosphere escapes as a fast, steady stream of solar wind that comes pouring out and sweeps across the planets. When that stream hits Earth, it rattles our magnetic field and produces recurring bouts of geomagnetic activity, the minor storms and aurora that show up like clockwork. Now here is the unusual part. Coronal holes like this are normally the signature of a cycle's declining phase. The years after the peak when the sun is winding down, they are not supposed to dominate the maximum, and yet this cycle has been ruled by enormous coronal holes, including ones that stretch right across the sun's equator, appearing at a time when, by the textbook, they should not be the main show. And one particular coronal hole has become almost a recurring character in the story of this cycle. It is a long-lived hole, a stable opening in the sun's atmosphere that has survived for something like a dozen full rotations of the sun. Remember that the sun rotates roughly once a month as seen from Earth, so this single feature has been swinging back around into view, firing its stream at us, sliding off the far side and coming back again, month after month, for the better part of a year. It shrank a bit, then grew again, and on its most recent passes it has been the engine behind a whole series of those recurring high-speed wind streams, including the one washing over Earth as I record this. A surface feature that stubborn, that persistent, that dominant during a phase of the cycle when it should be fading is not what a textbook quiet sun looks like. It is what a sun with an unusual magnetic organization looks like. And there is a reason that one stubborn coronal hole keeps showing up in this story, because the stream it fires at us is not just a curiosity, it is part of the preconditioning we're going to talk about later. Every time that hole rotates back into view and points its open chimney toward Earth, it sweeps that fast stream of solar wind across our magnetic field and keeps it agitated, restless, never fully settling back to a quiet baseline. Think of it like a hand that keeps giving a tense rope little tugs every 27 days or so, never hard enough to snap anything, but never letting the rope go slack either. A magnetosphere that is being regularly tugged like this is a magnetosphere that is easier to disturb, because it is already partway disturbed. It does not get to fully rest and rebuild its margin before the next nudge arrives. So when forecasters look at the calendar and see this hole coming back around again, they are not just predicting another minor light show, they are watching a sun that keeps our defences slightly off balance on a regular schedule, which is exactly the kind of background state in which a well-aimed eruption would do more damage than it would against a fully rested planet. The coronal hole is not the threat by itself, it is the thing that keeps the door from ever fully closing. There's also a quieter implication in how long this single feature has lasted, and it loops right back to the interior finding. A coronal hole is a place where the sun's magnetic field has organised itself into a stable, open configuration, and for that configuration to survive for a dozen rotations of the sun, to keep reassembling itself month after month rather than scrambling away as these features usually do, the underlying magnetism has to be unusually persistent and unusually organised. That is the same word that keeps coming up. Organised. The interior study found magnetism concentrating into a stable shell near the surface. The surface shows magnetism organising into a stubborn, long-lived hole and into rule-breaking spot regions. Whether or not those specific features are directly caused by the confinement the study measured, they are all symptoms of the same underlying theme, a sun whose magnetic field is arranged in a more concentrated, more persistent, less textbook way than we are used to. The interior and the surface keep rhyming, and the rhyme is always about organisation where we expected randomness. The second surface clue is in the spots themselves, in their magnetism. The sun follows some very reliable rules about how its magnetic regions are arranged. In each hemisphere, the spots tend to come in pairs with a consistent magnetic polarity, a leading end and a trailing end, and the arrangement reverses between the northern and southern halves and flips with each new cycle. It is one of the most dependable patterns in solar physics, but this cycle has produced an unusual number of regions that break the rule. Regions where the polarity is flipped or scrambled relative to what the cycle and the hemisphere say it should be. Even the most active, most complex region on the face of the sun right now shows this kind of mixed, partly reversed magnetic layout, with a powerful concentrated core where you would not normally expect it. These rule-breaking regions are magnetically tangled by their very nature, and tangled magnetic regions are the ones most likely to snap and flare. A sun producing an unusual crop of these is, again, a sun whose magnetism is organised in an unusual way. And there is a third clue, the most quietly ominous of the three, because it is about what we cannot see yet. In the same forecast discussions where the experts describe the current regions, they keep noting flares coming from just beyond the edge of the visible disk, from regions that have not yet rotated into view, regions still hidden around the curve of the sun on its eastern limb. We can catch the flash of a flare lighting up over the horizon of the sun before the spot that made it has even come around the corner. We can sometimes catch the loop structures and the magnetic loftiness of a region with our most advanced spacecraft while it is still on the far side. And right now, those over-the-horizon flares are telling us that there is active, complex territory rotating toward the Earth-facing side over the next few days. We do not yet know how strong it is. We just know it is coming round, already firing, before we can get a clean look at it. Now step back and take in all three clues at once. A coronal hole regime that belongs to a declining sun showing up to rule the maximum. A crop of spots breaking the magnetic rules more often than they should. Active regions firing off flares from behind the edge before we can even measure them. None of these on its own would mean very much. Solar physics has plenty of one-off oddities. But all three together, arriving in the same cycle that the interior study says has packed its magnetic engine into a thin near-surface shell, start to look less like a coincidence and more like a consistent story told by independent witnesses. The voice from inside the Sun says the engine has moved up and concentrated. The face of the Sun says its magnetism is organised in unusual, declining phase, rule-breaking ways, even at maximum. 2 languages, 1 message. Something about how this Sun is structured is genuinely different. I want to be careful here too, because I do not want to oversell a tidy narrative. The surface oddities I just described are real, but solar physicists would rightly tell you that any single cycle has its quirks, and that connecting the interior result to these specific surface features is interpretation, not proven fact. The study measured the interior. It did not declare that today's coronal hole or today's flipped polarity spot is caused by the confinement it found. So treat this part as me connecting dots that genuinely line up, while admitting that the line I am drawing through them is mine, not the paper's. That is the honest way to handle it, and it is the only way that keeps us anchored to what is actually known. But even with that caution, the convergence is remarkable, and it sets up the question that the rest of this video has to answer. If the Sun's engine has moved up and concentrated, and if the surface is showing us the signs of an unusually organised magnetism, then what about the eruptions? What about the actual clouds of plasma the Sun has been hurling our way? Because if this whole picture is right, you would expect those eruptions to look different too. You would expect them to come out tighter, narrower, more focused than the broad clouds we're used to. And the genuinely uncanny thing, the thing that made me want to make this video in the first place, is that for the last couple of weeks, that is exactly what they have been doing. The Sun has been firing eruptions that the forecasters expected to spread out and hit us, and instead they have stayed tight and slipped past. The forecast said a storm was coming. The storm did not come, and the reason it did not come is not comforting at all once you understand it. Part 6. The storms that keep missing. Let us go back to those 2 missed storms, because now we're ready to understand them properly. In the span of about 2 weeks, the official forecasters at the National Space Weather Center issued warnings that climbed to the strong level, the second highest tier they use, the level that means real geomagnetic disturbance. Aurora pushed down to middle latitudes and measurable strain on technology. In one case, an eruption came off a flare and the model showed it spreading out and clipping Earth. In another case, a whole cluster of strong flares, including some of the most powerful of the year, threw out their plasma and combined with that fast stream from the coronal hole, and the forecast called for a strong storm with the possibility of brief excursions to the next level up. By any reasonable reading of the launch, these should have been significant events, and then they simply were not. One of them gave us a faint bump as a shockwave brushed past, a little jump in the magnetic field with no real storm behind it. The other managed only a few hours at the moderate level before fading. Both of them, by the standards of what was forecast, were duds. So why did they fail? The answer is geometry, and it is the most important idea in this whole part, so I'm going to make sure it lands. When the Sun launches one of these clouds of plasma, the cloud does not necessarily come straight at us, and just as importantly, it does not come out as a uniform shell in every direction. It comes out as a structure with a shape and a width, and a direction of travel. And the punch it delivers to Earth depends enormously on that shape and that aim. Picture the difference between 2 ways of throwing a handful of sand. You can throw it as a wide, spreading spray, a fan that covers a broad arc so that no matter exactly where your target is, some of the sand catches it. Or you can throw it as a tight-packed clump, a narrow slug aimed at one precise point. The wide spray is forgiving. It does not need perfect aim, because it covers so much area that the target gets clipped almost no matter what. The tight clump is unforgiving. If your aim is even slightly off, the whole thing sails past and the target feels nothing. Solar physicists have language for this. A broad eruption aimed roughly at Earth is sometimes called a halo event, because as it expands toward us, it appears to swell into a glowing ring all the way around the Sun in our instruments, a sign that it is coming more or less in our direction and is wide enough to envelop us. That kind of cloud is the forgiving spray. It does not need a bullseye because it is enormous and diffuse, and even a glancing geometry still buries Earth inside the edge of it. But a narrow, tightly directed eruption is the unforgiving clump. It carries just as much energy, maybe more, packed into a smaller cone, and if that cone is pointed even a little to the side of Earth, The bulk of it goes screaming past into empty space, and we feel only the faint edge, the shock wave at the boundary, and nothing of the main body. And that is precisely what the records show happened with both of these recent storms. The bulk of the plasma stayed tightly directed, off to one side, and slid past our position, leaving us in the thin outer fringe where there is almost nothing to feel. There is a second, sharper edge to this confinement idea, and it is about time, about how much warning we would get. A broad, slow cloud announces itself. It takes its time crossing the gap, often a couple of days, and its sheer width means our spacecraft are likely to sample it cleanly and give the forecasters a solid read on what is coming. But the most dangerous version of a confined eruption is also usually a fast one, because the same launch that throws a tight, concentrated cloud tends to throw it hard, and a fast, narrow cloud is the worst of both worlds for anyone trying to see it coming. It crosses the distance in a fraction of the usual time, sometimes well under a day, which slashes the warning window. And because it is narrow, it can thread the gap between our monitoring spacecraft, or clip them in a way that gives a confusing partial reading, so that even the data we do get is harder to interpret. Remember that the Great Storm of 1859 made the crossing in roughly 17.5 hours, far faster than the typical 1 to 3 days. That speed was not a coincidence. It was a feature of a powerful, well-organised, concentrated launch, and it is exactly the kind of launch the new study hints this sun may be getting better at producing. So the confinement does not just make a direct hit harder, it potentially makes a direct hit faster, and a faster hit is one we would see coming later, with less time to protect the grid and safe the satellites. The narrow eruptions that keep missing us are quiet, partly because they are precise, and precision in the sun's aim is the one thing that should make a forecaster nervous, because the better the aim gets, the smaller the comfort in every near miss becomes. Now this is where I have to be careful about sourcing, and I'm going to be straight with you about it the way I always am. There is a growing observation circulating among the people who watch space weather closely, an idea making the rounds, that these recent eruptions have been coming out unusually confined, unusually narrow and columnated, more like that tight slug of sand than the broad forgiving spray. The argument is that the models keep expecting these clouds to balloon outward on the way to Earth, to spread into a wide front and catch us, the way clouds usually do, and that they keep failing to spread, staying tight and missing instead. I am repeating that observation because it is genuinely interesting and it fits everything else we have discussed, but I am not going to pin it to any one person or treat it as established fact, because it is not established fact. It is a pattern noticed across a small number of events, and a small number of events is not proof of a trend. 2 mist storms could just be 2 mist storms. The sun misses Earth all the time. So hold this as a hypothesis, a compelling one, not a conclusion. But here is why the hypothesis matters so much, and why I am willing to spend your time on it, even though the sample is small. Connect it to the interior study. The scientists found that the sun's magnetic engine has concentrated itself into a thin shell near the surface. We reasoned, as careful speculation, that a more concentrated engine might launch more concentrated eruptions. And now, in real time, the sun appears to be throwing eruptions that are behaving exactly as if they are more concentrated, tighter and narrower than the forecasters expect, missing because they are too compact to spread out and catch us. The interior measurement and the recent behaviour are telling the same story from 2 completely different directions. One is a 40-year acoustic study published in a journal. The other is a live pattern in the last 2 weeks of space weather, and they agree. That convergence is what elevates this from a curiosity to something worth taking seriously. And now I have to say the uncomfortable part out loud, because it is the whole reason this thread exists, and it is the moment where a mist storm stops being good news. A tight, narrow, confined eruption that misses Earth is reassuring only as long as it misses. Think back to the sand. The forgiving spray, the wide cloud, when it does hit you, hits you softly, because its energy is smeared across a huge area and diluted. But the tight clump, the narrow slug, when it does hit you, hits you hard, because all of its energy is packed into a small cone, and it slams into the target undiluted. The very thing that makes these confined eruptions miss so easily is the thing that would make a direct hit so much worse. A broad cloud aimed at Earth spends its strength across the whole sky, A narrow column aimed at Earth spends all of it on us. Nothing is wasted spreading out. It arrives concentrated, focused, the full charge delivered to a single point, and we are that point. So I need you to completely rewire how you feel about those two missed storms, because the instinct to feel relieved is exactly backwards. If the sun is genuinely entering a phase where its eruptions come out tighter and more focused, then the run of near misses we have been having is not the sun calming down. It is the sun rehearsing. It is the sun firing narrow, concentrated slugs of plasma past our position again and again, and the only reason we keep feeling nothing is that the aim has been off by a few degrees each time. A few degrees. That is the entire margin between a quiet night with no aurora and the kind of event we're going to spend the next part of this video describing, the kind that has happened before to people who never saw it coming, on a sun that looked just as calm as this one. The misses are not the good news. The misses are the dress rehearsal. And the only question that actually matters is what happens on the night the aim is true, because we have a very clear historical record of exactly what happens when one of these does not miss, and it is not a story about a faint aurora and a disappointed photographer. Let me make the geometry even more concrete, because the structure of one of these clouds matters, and it explains exactly what we felt during those misses. When a fast eruption barrels through space, it is not a single uniform blob. Out in front it drives a shock wave, a compressed wall of solar wind piled up ahead of it, the way water piles up at the bow of a ship. Behind that shock comes a turbulent sheath of disturbed material, and only behind that comes the main event, the tightly wound magnetic cloud itself, the part that carries the real punch, and the all-important magnetic orientation. Now think about what happens when a narrow, tightly aimed cloud passes off to the side of Earth. We can still clip the leading shockwave because a shock spreads wider than the cloud that drives it, like the wake of that ship fanning out far beyond the hull. So we feel a little jump, a brief compression of our magnetic field as the shock washes over us, and then nothing, because the main magnetic cloud, the dangerous core, sailed past in the dark to one side. That is exactly the signature the recent misses showed. A bump from the shock, and then quiet, because the body of the storm was never aimed at us in the first place. It is the fingerprint of a near miss by something narrow, and it is worth sitting with how thin that margin really is, because the difference between feeling only the shock and taking the full magnetic core is not some huge gulf. It is a matter of a few degrees of launch direction, a slight difference in where on the sun the eruption tears loose, a small shift in the moment of release relative to where Earth happens to be sitting in its orbit. We have been on the lucky side of that margin twice in 2 weeks. The margin does not know it is supposed to keep being kind to us. Part 7. What a direct hit looks like. In the late summer of 1859, a British astronomer named Richard Carrington was doing what he did most clear days, projecting an image of the sun onto a screen and carefully sketching the spots, when he saw something no one had ever recorded before. 2 brilliant points of white light flared up within a large, complex group of sunspots, blazing so intensely that for a moment he thought a beam of ordinary sunlight had broken through his equipment. What he was watching, without any way of knowing it, was one of the most powerful solar flares ever witnessed, and behind that flash, the sun had just launched a colossal cloud of magnetized plasma directly at the Earth. We have come to call the event that followed the Carrington event, and it remains, more than a century and a half later, the benchmark against which every solar storm is measured, the worst-case scenario written into the historical record. The cloud crossed the gap between the sun and the Earth with terrifying speed. A typical eruption takes 1 to 3 days to make the journey. This one made it in roughly 17.5 hours. That extraordinary speed is itself a clue worth holding on to, because a cloud that fast has very little time to spread out and weaken on its way across, which means it arrives more concentrated, more focused, carrying more of its launch energy intact. It was, in a sense, the historical example of exactly the kind of tight, fast, undiluted blow we were just talking about. And when it struck the Earth's magnetic field, it produced a geomagnetic storm of a magnitude we have struggled to fully reconstruct ever since, because our instruments at the time were primitive, but the best estimates place its strength far beyond anything in the modern record, in a class entirely of its own. The effects were unlike anything people of that era had a framework to understand. Aurora, the northern and southern lights that normally hug the polar regions, blazed down into the tropics. People saw them over the Caribbean, over Hawaii, over Colombia, places that essentially never see them. The glow was so bright in some places that gold miners woke in the middle of the night and began cooking breakfast, thinking dawn had broken. Birds began to sing. But the part of the story that matters most for us is what happened to the one piece of electrical technology that civilization had managed to build by 1859, the telegraph. The telegraph network was the internet of its day, a web of wires strung across continents, and those long wires were the perfect antennas for the currents that a great geomagnetic storm induces. Operators found their equipment going haywire. Sparks leaped from the machinery. Some operators received electric shocks. Telegraph paper caught fire. And in one of the most remarkable details in the entire history of space weather, some operators discovered they could disconnect their batteries entirely and keep sending messages using nothing but the current the storm itself was driving through the wires. The storm had energized the whole network with its own power. Now, I want you to notice the single most important fact about the 1859 event, the fact that ties it straight back to everything we have been building toward, because it is the fact almost every casual telling leaves out. The Carrington event did not happen during some monstrous record-shattering solar maximum. It happened during a cycle that was, by the count of spots, roughly average. A little above the middle, perhaps, but nothing exceptional. Nothing that would have made an astronomer of the day point at the sun and say, "Look out, that one is a monster." The most devastating solar storm in recorded history came from an ordinary-looking sun. Let that sink in against the backdrop of the study we have been discussing. We have just learned that our current sun looks ordinary by its spots, while hiding an unusual concentrated interior state. And the worst storm we have ever recorded came from a sun that also looked ordinary by its spots. The lesson of 1859 is that the spot count never protected anyone. And if you think 1859 was a freak, a 1 in 1,000 alignment that we can safely file away as ancient history, let me give you the event that should genuinely unsettle you, because it makes the same point even more sharply. In May of 1921, a great geomagnetic storm struck the Earth, and by some measures it approached the raw strength of the Carrington event itself. It set fires in telegraph and railroad signal equipment, knocked out communications, and lit up the sky with aurora far outside their normal range. It was, without question, a major storm, one of the strongest of the 20th century. And here is the detail that should change how you think about all of this. That storm struck when the sun's spot number was around 37. 37. It happened late in the declining phase of a weak cycle, on a sun that by every surface measure was winding down, going quiet, nearly asleep. A nearly spotless sun produced a storm that rivaled the most catastrophic one in history. So now lay the two facts of this video side by side, because together they form an argument that is hard to walk away from. Fact 1. From the new interior study, the sun can look quiet on its face while its magnetic engine is in an unusual, concentrated state underneath. Fact 2. From the historical record, a quiet-looking sun has already produced storms that rival the worst we have ever seen, more than once, including one on a spot count of just 37. The first fact tells us our main reassurance, the calm-looking surface, can be camouflage. The second fact proves that the camouflage has fooled us before, at the worst possible moments, in the most literal way, because the storms came anyway. The thing we keep using to feel safe, the modest spot count of the current cycle, is the exact condition under which the most dangerous storm of the 20th century arrived. This is the moment where the whole picture should tighten in your chest a little, and I want it to, because the fear here is earned, not manufactured. We're not looking at a sun that is obviously visibly enraged, throwing record numbers of spots and screaming danger. That would almost be easier, because we would all see it coming. We are looking at a sun that looks calm, that the headlines call modest, that the spot count files under ordinary, while a 40-year acoustic study tells us its engine has crept up and concentrated into a thin shell, while its recent eruptions come out unusually tight and keep just missing, and while history screams at us that quiet-looking suns are exactly the ones that have delivered the great blows before. Every piece points the same way. The surface calm is not a promise, it is the precondition. But here is the thing that separates 1859 and 1921 from the threat we actually face today, and it has nothing to do with the sun. The sun in those years was firing at a world of telegraph wires and railroad signals, a world where the worst a great storm could do was burn some equipment and frighten some operators. The sun has not changed its capabilities since then. It could throw another Carrington-class blow at any time, and the new study suggests we should be paying closer attention, not less. But the target has changed beyond recognition. The world the sun would hit today is not a world of telegraph wires. It is a world that runs completely and without any backup on a single fragile thing, and the last time a great storm hit the modern version of that thing, it took the lights out for 6 million people in about the time it takes to read this sentence aloud. And if you still want to believe that 1859 and 1921 were the absolute ceiling of what our sun can do, the longer record takes even that comfort away. By reading the growth rings of ancient trees and the layers of polar ice, scientists can detect the chemical fingerprints that a truly enormous blast of solar radiation leaves behind when it slams into our atmosphere, and those records contain spikes that dwarf anything in this era of human instruments. The most famous of them, buried in tree rings from the 7th and 8th centuries, points to a surge of high-energy particles so large that a storm of that class arriving today is almost too grim to model honestly. These monster events are rare, far rarer than a Carrington-class storm, but they are not zero, and they prove that the sun has a higher gear than anything we have personally witnessed. The point is not to frighten you with the worst imaginable case. The point is that our lived experience, even stretching back through the whole telegraph and satellite age, is a tiny and possibly unrepresentative sample of what our star is actually capable of. We have been watching closely for less than a single human lifetime in the grand scheme of solar history. The sun has been doing this for billions of years, and the record it left in the trees and the ice says plainly that it can reach further than we have ever seen it reach. So when we ask whether a quiet-looking modern sun could surprise us, the honest answer from the long record is not just yes. It is that it has done far worse than our worst, and it did not need our permission or our attention to do it. Part 8. 90 Seconds and the Wires We've Strung Since. In the early hours of March 13th, 1989, the people of Quebec were asleep when their world went dark. A great solar storm, born from a giant tangled group of sunspots, had been pouring energy into the Earth's magnetic field for hours, and at around 2:30 in the morning the strain finally found the weakest link in the chain. The province's main power grid, the system run by Hydro-Quebec, did not flicker or sag or brown out gracefully, it collapsed. In roughly 90 seconds from the first protective trip to total failure, a grid carrying around 21,000 megawatts of power fell over, and about 6 million people lost electricity in the dead of a subarctic winter night. It stayed down for about 9 hours. Transformers were damaged. The cascade was so fast that no human operator could have reacted in time, because the whole thing happened faster than people can think. 90 seconds. That is the modern world's most famous lesson in what a solar storm can do to an electrical grid, and it was not even a Carrington-class event. It was substantially weaker than 1859. It just happened to hit a vulnerable system in exactly the wrong way. The region of the sun that did it is worth knowing about, because it teaches a lesson about timing that connects directly to our story. The source was a sprawling, magnetically complex group of spots, a genuine monster of a region, and it did not deliver its blow in a single clean punch. It put on a barrage. As it crossed the face of the sun, it fired off an extraordinary number of flares, including many of the strong class and several of the very strongest class, an almost relentless bombardment over a stretch of days. And here is the mechanism that matters. Days before the main grid-killing storm, while that region was still near the edge of the sun, it threw out an enormous flare whose radiation washed over the Earth's upper atmosphere and charged it up, energized it, primed it. So by the time the main clouds of plasma arrived a few days later, they were not hitting a calm, rested magnetosphere. They were hitting one that had already been agitated and preconditioned by the earlier blast. The storm landed on a system that had been softened up first, and the combination hit far harder than either piece would have alone. Stacking and timing. An earlier blow that opens the door and a later blow that comes through it. Remember that, because the sun right now has active regions firing in sequence, and a stable coronal hole stream already agitating our magnetic field, setting up exactly the kind of preconditioned background where a well-aimed eruption would land on an already rattled planet. Now, The mechanism that actually takes down a grid is worth understanding clearly. Because once you understand it, you understand why this threat is so specific and why some of the scarier rumours about it are wrong. A geomagnetic storm makes the Earth's magnetic field swing and lurch, and a changing magnetic field induces electrical currents in any long conductor sitting inside it. The key words are long conductor. The currents are gentle and slowly varying, almost like a direct current pushed through the system, and they are weak per meter. But a high-voltage transmission line is not a meter long. It is hundreds of kilometers long, and across that enormous span, the gentle induced push adds up into a substantial unwanted current that comes flooding into the grid through its grounded points. That current pours into the great transformers at the hearts of our substations, the massive machines that step voltage up and down, and it drives them into a state called saturation, where they overheat, hum, vibrate, and can be damaged or destroyed. That is the kill chain. Storm shakes the field induces current in the long lines, current saturates and cooks the big transformers, and the reason that is so frightening is not the blackout itself. Blackouts get fixed. The reason it is frightening is the transformers. The largest of these machines, the extra high voltage transformers that anchor the backbone of the grid, are not sitting on a shelf somewhere waiting to be swapped in. They're enormous. They're often custom built for their specific location. They can take many months to a year or more to manufacture, and we do not keep many spares. A storm that damages a handful of them in one region is a long, ugly outage. A storm that damages many of them across an entire continent at once is a catastrophe, measured not in hours or days, but in months and possibly years, because you cannot quickly replace what takes a year to build and was never stockpiled. An assessment by the National Academy of Sciences back in 2008 tried to put a number on a truly severe event, and landed on a first-year cost on the order of $1 to $2 trillion, with a recovery stretching 4 to 10 years for the worst-hit areas. That is the shape of the worst case, not a long night, a long emptiness, and here is the part that should genuinely keep you up, because it is the part that has gotten worse every single year since 1989 while almost no one was paying attention. The grid that a great storm would hit today is not the grid of 1989. It is older, much of its core infrastructure decades past its design life, and it is being asked to carry far more load than it was ever built for. Consider just one project, because it is a perfect emblem of the trend. Earlier this year, the federal government announced a partnership to build an enormous data center campus on the site of a decommissioned uranium plant in southern Ohio, near a town called Piketon. The plan calls for a data center drawing about 10 gigawatts of power, with up to 10 gigawatts of new generation to feed it, including more than 9 gigawatts of new natural gas plants, backed by billions of dollars in grid and transmission upgrades. To give you a sense of scale, the entire state of Ohio runs on something like 30 gigawatts at its summer peak. So this one campus, this single facility, is contemplating power on the order of a third of the whole state's peak demand. And it is not alone. Projects like it are being announced across the country and around the world, driven by the explosion of artificial intelligence and the staggering hunger of the computers that run it. Think about what that means in the context of everything we have discussed. We are bolting unprecedented new load onto an aging grid, tying these massive new demands into the existing network rather than walling them off behind their own dedicated, isolated power. We are making the system bigger, more interconnected, more strained, and more essential to daily life all at the same time, precisely as a 40-year study tells us the sun's magnetic engine has migrated into an unusual concentrated state, and precisely as the sun shows us, in real time, that it is throwing tighter, more focused eruptions that keep just missing. The exposure has never been higher, and it is climbing on a steep curve while the threat may be quietly sharpening overhead. And the grid is only half of what we have put in harm's way, because we have also filled the sky. The last time a great storm hit the modern world in 1989, there were a few hundred satellites in orbit. Today there are tens of thousands, and a single company's constellation alone accounts for more than 10,000 of them, swarming in low orbit just above the atmosphere. A severe solar storm does brutal things to that environment. It heats and puffs up the upper atmosphere, which increases the aerodynamic drag on every low-orbiting satellite, dragging them down, scrambling their tracking, and we have already watched smaller storms knock newly launched satellites out of the sky this way. It floods them with charged particles that bury themselves far inside the electronics and trigger damaging internal discharges. It disrupts the satellite-based navigation and timing signals that the entire modern economy quietly runs on, from your phone's map to the timestamp on a financial transaction to the synchronization of the power grid itself. So a great storm today would not just threaten the wires on the ground, it would threaten the constellation overhead at the same moment, knocking out two of the pillars civilization leans on in the same few hours. So here are the two halves of the risk, and I want to set them right next to each other, because this is the connection the whole video has been building toward. On one side, a sun whose magnetic engine has, by the best new measurement we have, concentrated itself into a thin near-surface shell, behaving in ways that suggest its eruptions may be growing tighter and more focused, on a face calm enough to keep fooling us. On the other side, a civilization that has wired itself together more tightly, loaded its aging grid more heavily, and filled its sky more densely than at any moment in its history, and is accelerating in that direction by the month. A changing sun and a maximally exposed Earth are not two separate stories. They are the two halves of a single risk, and they have been moving toward each other the whole time. The only thing standing between those two halves is a few degrees of aim, and aim, as we have seen all night, is the one thing that can change in an instant. I want to make the transformer threat vivid, because it is abstract until you picture it, and it is the hinge the whole catastrophe turns on. In that 1989 storm, the damage was not confined to Quebec. Far to the south in New Jersey, a large transformer at a power station was cooked by the same storm, its insulation damaged beyond repair, taken out of service permanently. One storm, one transformer, in a place that did not even lose power that night. Now, multiply that. In a truly severe, well-aimed event, the induced currents would not pick on one machine in one state. They would surge through long transmission lines across an entire continent at once, pushing dozens or hundreds of these giant transformers toward the edge in the same few hours. And remember what these machines are. They are not parts you order and install in an afternoon. The largest of them are custom engineered, often built overseas, weighing hundreds of tons, with manufacturing queues that can stretch beyond a year even in normal times, and we keep only a thin reserve of spares. A blackout where the wires simply tripped offline can be restored in hours once the storm passes. A blackout where the transformers themselves are physically destroyed across a continent is a fundamentally different kind of disaster, because you cannot turn the lights back on until you have rebuilt the machines, and you cannot rebuild them quickly when the factories that make them are an ocean away and already backlogged. That is the scenario that turns a bad night into a bad year, and the sky has already shown us, recently and cheaply, that the satellite threat is not hypothetical. A couple of years ago, a batch of newly launched satellites was lost almost immediately after reaching orbit, because a relatively minor geomagnetic storm, nothing remotely close to a great one, puffed up the upper atmosphere just enough to increase the drag on them, and they could not climb to a safe altitude before they were dragged back down to burn up. That was a small storm taking out a small number of satellites. We now have tens of thousands of satellites threaded through low orbit, and the modern world quietly depends on them for navigation, for precise timing, for communication, in ways most people never think about until the signal fails. A great storm would not gently nudge that environment. It would heave the whole upper atmosphere outward, scramble the tracking that keeps thousands of these spacecraft from running into each other and the debris around them, and flood their electronics with charge. The grid below and the constellation above are exposed to the very same event in the very same hours, and we have stacked more onto both than any generation before us. Part 9. Right Now, and What It Isn't. Let me bring all of this down to the ground, to this exact moment, because while we have been talking about 40-year studies and historical storms, the sun has not stopped. As I record this, there is a live geomagnetic stormwatch in effect for tomorrow. The forecasters have flagged the 13th of June for a moderate-level storm, driven by that persistent stream of fast wind pouring out of the long-lived coronal hole, combined with the arrival of a couple of clouds of plasma that left the sun on the 9th and the 11th. The numbers point to a storm that should push the planetary disturbance index up into moderate territory, with Aurora potentially visible as far south as a line running roughly from New York to Wisconsin to Washington state. The The solar wind is already running fast. The magnetic field carried in it has been pointing southward, which is the orientation that lets energy pour into our defences, and that complex, partly rule-breaking region we talked about is rotating toward the centre of the sun's face, toward the line of fire that points straight at Earth. I want to be clear and calm about this particular forecast, because clarity is the antidote to both panic and complacency. Tomorrow's storm is not the big one. A moderate storm is a real event worth watching, capable of producing beautiful aurora and minor effects, but it is not a grid killer, and it is not a Carrington event. If you take nothing else from this part, take that. I am not telling you to brace for impact tomorrow. What I am telling you is that the conditions we have spent this whole video describing are not abstract. They are live. A concentrated interior, a dominant coronal hole, complex regions rotating into firing position, a magnetosphere already being agitated by the stream, and active territory firing from behind the limb before we can measure it. This is the preconditioned, primed background we discussed, the kind of stacked setup that, in '89, turned a strong storm into a catastrophe. Tomorrow it will likely just give us a nice aurora, but it is a snapshot of exactly the kind of state in which a well-aimed, tightly focused eruption would find an Earth that has already had its guard lowered. Now I have to do the part of this video that I consider the most important part, even though it is the least dramatic, because this subject attracts an enormous amount of nonsense, and if I let the nonsense ride along with the real science, I poison the real science. So I'm going to take the most common false claims attached to this topic, one by one, and tell you plainly what is true and what is not, because you deserve to walk away from this with a clear head, not a head full of fog. The genuine threat is serious enough on its own. It does not need to be inflated, and inflating it only makes it easier for people to dismiss the whole thing. The first false claim is that a solar storm will fry your car, your phone, the electronics in your pocket, like some kind of electromagnetic pulse from a science fiction movie. This is wrong, and understanding why is genuinely reassuring on a personal level. A geomagnetic storm is not a nuclear electromagnetic pulse. A nuclear pulse delivers a sharp, fast, high-frequency burst that can couple into small circuits. A solar storm does the opposite. It induces slow, gently varying currents, and those currents only build up to dangerous levels across very long conductors, hundreds of kilometers of transmission line, long pipelines, the great spans of the grid. Your car is not hundreds of kilometers long, neither is your phone. The induced current in a short circuit like that is negligible. When you heard that telegraph equipment caught fire in 1859, remember that the telegraph was a network of immensely long wires strung across whole countries, which is exactly the kind of long conductor that does pick up these currents. Your laptop is not a transcontinental telegraph line. The real victims of a solar storm are grid transformers and satellites, not the gadgets in your house. So please, set that particular fear down. It is the wrong fear, and carrying it just makes the real risk harder to see. The second false claim is that the planets are steering the sun, that the alignments of Saturn or Uranus or Neptune are what drive the solar cycle and trigger these storms. I understand the appeal of this idea, because there is something deeply human about wanting the heavens to move in meaningful patterns, and the timing of certain alignments can look suggestive if you go hunting for it. But the physics does not support it, and it is not a close call. The gravitational tug the planets exert on the sun is real, but it is staggeringly weak, orders of magnitude too feeble to reorganize the churning magnetic engine of a star. The correlations that people advance for this idea tend to fall apart under statistical scrutiny, and crucially, they have no working mechanism behind them. And notice, importantly, that the scientists who actually did this interior study attribute the change they found to the sun's own internal dynamo, to processes far within the star itself, not to the planets. The engine is internal. The sun is not a puppet on planetary strings. It is a self-driving machine, and the change we found is the machine reorganizing itself from within. The third false claim is one we have addressed on this channel before, and I'm going to hold the same firm line I always have, because intellectual consistency matters. The claim is that solar storms trigger large earthquakes, that the coronal holes and the storms are setting off the big quakes through some chain of cause and effect. And I want to be respectful here, because I know this idea has a strong pull, and I know people notice that big quakes sometimes follow space weather. But noticing that two things sometimes happen near each other in time is not the same as showing that one causes the other. The statistical case for this connection is weak and inconsistent. The energy budget does not work. The amount of energy a storm couples into the ground is trivial compared to the colossal forces locked in a fault. There is no solid mechanism, and there are plenty of clear counterexamples. Enormous earthquakes that struck while the sun was completely quiet, and quiet ground during powerful storms. Earthquakes happen because of the slow, immense grind of the plates, the strain building up over years and decades until a fault finally ruptures. The sun does not pull that trigger. Temporal coincidence is not causation, and on this channel we do not pretend it is. And I want to add something hopeful here, in the middle of all this clearing away of nonsense, because once you set down the false fears, there is something genuinely empowering left in your hands. The reason all of these false claims fall apart so easily is that the real science is open, and open science is something you can actually watch for yourself. You do not have to take my word, or anyone's word, for what the sun is doing. The same dashboards the professionals use are public and free. You can pull up the live solar wind readings, the same numbers I have been quoting, and watch the speed and the magnetic direction update through the day. You can see the storm watches the moment they are issued. You can look at the latest images of the sun's face and pick out the active regions and the coronal holes for yourself. None of it is locked behind a wall, and that turns this whole subject from a source of helpless dread into something you can have a real, informed relationship with, the way some people follow the weather or the tides. The antidote to being frightened by something you do not understand is not to look away from it. It is to learn to read it. A person who checks the space weather the way they check tomorrow's forecast is not a person living in fear. They are a person who would simply know, a day ahead, if something genuinely big were inbound, and who could then do the few sensible things that actually help. Knowledge is not the thing that makes this scary. Knowledge is the thing that takes the fear and turns it into readiness. So when I tell you to take this seriously, I'm not telling you to be afraid, and I'm certainly not telling you to fall for any of the louder, wilder stories that swirl around this topic. I am telling you the opposite. I am telling you that the real version, the careful, open, measured version, is both more interesting and more manageable than the nonsense, and that the people who understand the real version are the ones who will be calm and prepared on the day the rest of the world is panicking over a blackout they do not understand. Clear away the fog, and what is left is not a reason to despair. It is a reason to pay attention. The fourth false claim is that someone is hiding this, that there is a secret incoming superstorm or a suppressed forecast that the authorities are keeping from the public. This one falls apart the moment you look, because the entire field is built on open data. The storm watches are posted on public dashboards in real time, updated through the day, free for anyone to read. The spacecraft imagery is public. The interior study we have spent this whole video on was published in an open scientific journal and written up by the university that did it. There is no hidden forecast. The watch for tomorrow's storm went out to everyone at once. If anything, the problem is the opposite of suppression. The information is all right there in the open and almost nobody's looking at it. The danger is not concealment. The danger is inattention. And the fifth false claim runs in the completely opposite direction from everything we have discussed, which is that the sun is shutting down, sliding into a grand minimum, a decades-long slumber like the one that gripped it in the 17th century. I bring this up because some people will hear weak surface, modest spot count, and leap to the conclusion that the sun is going dormant. But that is not what the data shows at all. This cycle actually overperformed its own predictions, and it has been more active than the weak cycle before it. The interior study did not find a sun winding down. It found a sun whose magnetism has reorganized and concentrated, which is a structural change, not a shutdown. Whether some future minimum is coming is a question we genuinely cannot answer until we see how the next cycle behaves, and anyone who tells you with certainty that the sun is going to sleep is guessing. The honest reading of this cycle is not a sun fading out. It is a sun rearranging itself in a way we are only just learning to detect. So clear all of that away. Set down the car-frying pulse, the planetary puppet strings, the earthquake trigger, the secret hidden forecast, the imaginary shutdown. When you sweep the nonsense off the table, what remains is not less frightening. It is more, because it is real, and it is specific, and it is supported by exactly the kind of careful, open, peer-reviewed science we should actually trust. What remains is a quiet, measurable change beneath the surface of our star, a pattern of tightly focused eruptions that keep just missing, and a civilization that has never been more exposed to the one that lands. That is the real signal, and now that the noise is gone, the only question left is the one that actually matters. Knowing all of this, how worried should we genuinely be? And what, if anything, are we supposed to do with that worry? Part 10. Would we even see it coming? There is a phrase you will hear constantly attached to this subject, and I have been deliberately holding it back until now, because it is usually used carelessly, and I want to use it carefully. The phrase is that we are overdue for a great solar storm. People say it the way they might say a bus is overdue, as if there is a schedule, and the storm is late, and any minute now it must arrive. That is the wrong way to understand it, and I do not want you walking away with a countdown clock in your head, because that is not what the science says. Carrington-class events appear to come along on a timescale of roughly once or twice a century, give or take, based on the handful we can identify in the historical and geological record. The last unambiguous one was in 1859. We have had major near misses since, including a monster in 2012 that erupted from the Sun and crossed Earth's orbit, but happened to do it when our planet was somewhere else. A blow that would have rivaled Carrington if the timing had been a week different. So when someone says overdue, what they really mean, when you strip out the false sense of a schedule, is simply this. The base rate is not zero, it is not even small on the timescale of a human life, and a long quiet stretch does not lower the odds of the next one. It is a statement about probability, not about a clock ticking down to a known hour. So let me give you the honest synthesis, the most accurate summary I can build from everything we have walked through, with every uncertainty left intact, because you have earned the real version and not a tidy one. We have a new, careful, peer-reviewed measurement telling us that the magnetic engine of our Sun has concentrated itself into a thin shell near the surface, in a way it has not done in the 40 years we have been able to listen. We have a chain of reasoning which I have labelled as speculation at every step, suggesting that a more concentrated engine might produce more concentrated eruptions. We have a live, real-world pattern of recent eruptions coming out unusually tight and missing us, which fits that reasoning but rests on a small number of events. We have a historical record proving beyond any doubt that quiet-looking suns have delivered catastrophic storms before, including one on a spot count of almost nothing, and we have a civilization more exposed to such a storm than any that has ever existed, growing more exposed by the month. Lay those facts in a row, and the conclusion is not that doom is scheduled. The conclusion is more uncomfortable than that, because it is uncertain. The conclusion is that the risk is real, elevated, and genuinely hard to quantify, layered on top of the highest stakes in history, with new evidence that the instrument we have always trusted to warn us may be partly blind to the very change that matters. And I have to be equally honest about the other side of the uncertainty, because intellectual honesty cuts both ways, and I will not stack the deck even toward a conclusion I find compelling. We do not actually know that a near-surface, concentrated magnetic engine makes great storms more likely. It is possible, genuinely possible, that this confinement does something else entirely, that it changes the character of the cycle in ways that are neutral, or that even reduce the odds of a direct catastrophic hit. The scientist who made this discovery did not claim it points toward a superstorm, and I am not going to put words in their mouths. What they gave us is a measurement of a change, not a prediction of a disaster. The honest position, the only position the evidence actually supports, is that we have found something genuinely new about how our star is organized, that it raises serious questions about whether our oldest warning instinct is still reliable, and that we do not yet know which way it cuts. Uncertainty in both directions. That is the truth, and the truth is allowed to be unresolved. But here is what I find, strangely, almost steadying about all of this. And it is where I want to leave you, because I do not believe the right response to any of this is dread. The right response is the oldest and most human one there is, which is to look clearly at a real risk and prepare for it rather than pretend it away. Everything we have talked about tonight is, in the end, a solvable problem on our side of it. The grid does not have to be this fragile. The great transformers can be hardened against induced currents, and they can be stockpiled as spares so that a damaged region can be brought back in weeks instead of years. Operators can be warned, and modern forecasting gives us at minimum the better part of a day's notice before a cloud of plasma arrives, time enough to take protective action, to shed load, to safeguard the most critical machines. Satellites can be put into safe modes when a storm is inbound. Navigation and timing systems can be backstopped. None of this is science fiction. All of it is engineering we already know how to do. The only thing standing between us and a far more resilient world is whether we decide to spend the attention and the money before the storm rather than after it. And on the most personal level, the level of you and your own household, the lesson is not to be afraid. It is simply to be the kind of person who is not helpless when the power goes out, whatever the reason. The same modest preparations that carry a family through an ordinary winter storm or a summer grid failure, a way to keep a phone charged, a way to keep a refrigerator cold for a while, some water, some light, a little resilience built in before you need it, are exactly the preparations that matter in the worst case too. You do not need to live in fear of the sun to keep a flashlight and a plan. Preparedness is not panic. It is the opposite of panic. It is what lets you watch a sky full of aurora with wonder instead of terror, because you know that whatever happens, you and the people you love are not going to be caught completely flat-footed. So let me bring this all the way back to where we started, to the thread that has run through every part of this. We began with a paradox, a sun that kept being forecast to strike and kept missing, and a quiet face that the spot count called ordinary. And we have arrived somewhere very different from where that paradox first pointed. We have learned that the calm of the sun's surface was never the same thing as safety. We have learned that beneath that calm face, in a thin shell barely 1,000 kilometers thick, the magnetic engine of our star has crept upward and concentrated itself in a way we have only now developed the ears to hear. We have learned that the storms that keep missing may not be the sun calming down, but the sun firing tighter and tighter, the aim off by just a few degrees. And we have learned that history is unambiguous that a quiet-looking sun has delivered its worst blows before to a world far less exposed than ours. The danger, in the end, was never that the sun would look angry. If the sun looked angry, we would all see it coming, and we would act. The real danger, the one this whole story circles back to, is that the sun can look calm right up until the moment it does not, and that we have spent a century training ourselves to read safety in exactly the kind of calm that has fooled us before. We finally learned how to listen to the inside of our own star, to press our ear against it across 4 decades and hear the slow, low changes moving through its interior. The sun has been telling us something. The question that should keep us honest and watchful and quietly prepared is whether we are going to act on what we heard, or whether we are going to wait, comfortable in the false reassurance of a quiet-looking face, until the day our star stops whispering and decides, finally, to speak for itself.